using mathematical induction. This is going to be a little bit of a strange approach to the proof, but it's kind of cool too. To get this proof going, I'm going to let us assume a couple of items of calculus knowledge. First of all, we're actually going to assume the product rule works. Remember, the product rule is a rule for differentiating products of functions. It says that the derivative of two functions multiplied together, say f and g, would be the derivative of f times g plus f times the derivative of g. Now you might be thinking it's kind of weird to assume the product rule works if we're going to prove the power rule, right? Because isn't it true that the power rule comes first in the calculus book? That's true, but if you think about it, and back to when you learned the product rule, you didn't really need the power rule to prove the product rule. So in fact, you could cover the product rule first if you wanted to. So we're going to assume that the product rule works in this proof. And we're also going to assume that the derivative of x, just by itself, the derivative of x is 1. And that's safe to assume as well for a couple of reasons. For one thing, we could always go back to our limits, for example, and just prove that the limit as h goes to 0 of x plus h minus x over h is 1. And that's one way we could do it. Or we could think of this graphically. The function y equals x is just the straight line that has slope 1 that goes to the origin, and so the derivative tells us the slope, and so the slope is 1. Either way, that assumption is safe to make here at the beginning, and it's also actually safe to assume the product rule. So let's assume both of those things are true, and if we wanted to prove those, then we could go back and do a little more work. Now let's move on to the actual proof of the power. Okay, so in the base case here, we want to show that our predicate, which just to remind ourselves, the predicate we're working with here, the p of n, is that the derivative of x to the nth power is equal to n times x to the n minus 1. That is going to be our quote-unquote p of n in this proof. So what we're going to do is show that in the base case here is we're going to show that p of 1 is true. We want to show that the derivative of x to the first is 1 times x to the 1 minus 1. Well, let's just deal with each side individually here. On the left-hand side, we know based on what we're allowed to assume that this derivative is equal to 1. On the right-hand side, what we have here is 1 times x to the 0, and that is also equal to 1. So those two guys are equal to each other, and so the base case is established. Again, we had to make an additional assumption in this problem right here using some basic calculus knowledge, but I think that's a safe assumption to make here. So the base case is established. So let's move on to the inductive step now. The inductive hypothesis, the thing that we're going to assume is that for some positive integer k, the power rule holds. So the derivative of x to the k, sorry, let me erase that. The derivative of x to the k power is k times x to the k minus 1. This is what we're assuming as we move forward in the proof, that I've made it up to the kth step, and now I've got to pay off the gnomes again to let me up to the next step. So what are we going to try to prove here? Well, we're going to take the proposition, the predicate, I should say, and replace the k with a k plus 1. So we need to prove that the derivative of x to the k plus 1 is, now wherever I see a k, here or here or here, I'm replacing this with a k plus 1. So let me do this in a different color. That would be k plus 1, parenthesis, times x to the, that used to be a k right here, but I'm going to replace it with a k plus 1. And there was already another minus 1 there to begin with, so I have to subtract off the 1. So to simplify that expression, I'm going to prove that the derivative of x to the k plus 1 is k plus 1 times x to the k. So again, you got to be very careful about what you want to assume. This is our assumption, and this is what we're trying to show. And these two things do not mix together. Okay, we keep them separate. So let's move on to another slide and prove what we need to prove. And again, we actually have 3 assumptions in the game at this point. We're assuming the inductive hypothesis, this stuff in here, and also the 2 facts about the product rule, which we haven't seen that show up yet, and also the rule about the derivative of x itself. So let's start, and we'll begin. So we're trying to prove an equation. We're trying to prove the power rule for x to the k plus 1. So let's start with just the left-hand side of that expression. Eventually I know what I need to get on the right-hand side, but I don't know that I'm there yet. So what I'm going to do here is pull in some things that I know. I'm going to, first of all, work inside the square brackets. Okay, inside the square brackets, I can replace x to the k plus 1 with x to the k times x, okay, just to split off one factor of x there using my exponent rules. If it helps, you can just stick a 1 exponent on there. And now you know what I've got here is a product of two things. So let me use the product rule to break this up. Now the product rule says that the derivative of my product is going to be the derivative of the first guy, so derivative of x to the k, times x plus x to the k times the derivative of x. Okay, this is the good old-fashioned product rule at work here. Now, we're actually really close to the end here because I can use my inductive hypothesis to rephrase this. Okay, I have the derivative of x to the kth power, and my inductive hypothesis, I'm going to make this in green here. I'll make the equal signs in blue, I guess, but I'll make everything else in green. The inductive hypothesis says that this expression right here is going to be kx to the k minus 1. Okay, that's the inductive hypothesis working for you. Everything else up here is either going to be something that was already there, like the times x or the plus x to the k, or an additional assumption. That we, for example, we said that it's okay to assume that that derivative right there is equal to 1. Now let's try to just work through all the math here. On the left term of this expression, I have an x times an x to the k minus 1. If I combine those two terms, I'll have the k being there, but the two x's multiplied to give me kx to the kth power. Okay, that's all this stuff comes from there. And then I had plus 1 times x to the k, so that's just this. Now what you notice here is that I have a factor of x to the k and another factor of x to the k, so let's pull that factor out. And I'd have k plus 1 times x to the k. Well, that's what I wanted to show, right? I wanted to show that the derivative of x to the k plus 1 is k plus 1 times x to the k. If you go back to the previous slide, that's exactly what I wanted to show, and I've done it. I started with the left-hand side, split this up using algebra, then split things up this way using the product rule, which I'm allowed to assume. This is using the inductive hypothesis and the fact that I know what the derivative of x is. And the rest of it is algebra and then algebra. So all those steps are justified, and that is the end of the proof because I have done the base case already. That was pretty simple. And now I've done the inductive step. I assumed that the power rule is true for n equal to k, and I've proven that it's true for n equals to k plus 1. So I've climbed the calculus stairwell and actually proven the power rule, which is pretty nice. Now, if you wanted to prove the power rule for non-integer powers, we often use things like x to the 3/2, and this you'd have to have a completely different proof for that. But this induction proof establishes it for positive integer powers of x, and so there you have unlocked one of the mysteries of calculus. Congratulations.